Okay, the last speaker is Mr. Chong-Yan Chen, who is currently working as a PhD student at the National Cheng University. He received his Bachelor of Science degree in 2020 from National University of Kaohsiung. His research is focused on how white spot syndrome virus modulate and facilitates de novo nucleotide synthesis in shrimp to promote viral pathogenesis. So his presentation today is about glucose and glutamine contribute to de novo nucleotide synthesis to support viral pathogenesis. Thank you very much. Please take the floor, Mr. Chen.
Hello everyone, I'm Eric, PhD student from NCKU Taiwan, and it is my pleasure to introduce my investigation. Glucose and the glutamine contributed to de novo nucleotide synthesis to support viral pathogenesis. So, as you know that white spot syndrome virus, WSSV, is a lethal shrimp virus, can cause 100% of mortality in a week after infection. And thanks for omics technology, we can investigate the global shrimp responses after WSSV infection and trying to identify the possible mechanisms which benefit to WSSV replication. And as you can see, during these 10 years, by using the omics approaches, our team has identified the diversity genome replication stage and the late stage of virus replication. So in the replication stage, diversity infection activates the aerobic glycolysis and glutamine metabolism and lipid beta metabolism for benefit in replication. And notably is that the host RAS PI3K-AKT-mTOR pathway, it seems to be a major modulator for regulating this WSSV-induced metabolic reprogramming. However, we still miss several puzzles such as the de novo nucleotide synthesis, and therefore it is my topic today. So, a series of studies have been shown that not only the production of nucleotide for mRNA expression or genome replication, the activation of de novo nucleotide biosynthesis also contribute to the production of NADPH. And NADPH is involved in the fatty acid biosynthesis and the reduction of the oxidative stress to maintain the reductive cellular environment. So in the novel nucleotide synthesis, you can see glucose right here and the glutamine right here and here. They can be the resources in this pathway. So later we will focus on the pentose phosphate pathway, purine biosynthesis, and the pyrimidine biosynthesis. So first of all, we are wondering about the importance of de novo nucleotide synthesis during WSSV infection on the transcriptomical level. So you can see with our transcriptomic database contribute, we select the critical genes that involve in the de novo nucleotide biosynthesis and to see the correlation network with other WSSV affected shrimp genes at the different time points during WSSV infection. So right here, as you can see, among this time point after WSSV infection, the target genes that involve in the de novo nucleotide biosynthesis show the stronger correlation with WSSV affected host genes. So we infer that the de novo nucleotide biosynthesis may be critical during WSSV replication. And next, we also found that the mRNA expression of genes involved in the pentose phosphate pathway, G6PD-H and the TKT, was significantly upregulated at the WSSV genome replication stage. And subsequently, we also investigate the several key genes that involve in the biosynthesis of purine and the pyrimidine after WSSV infection. And as we expected, the significant increase in the mRNA expression was also observed at the 12 hours post-injection. So next, in order to evaluate the de novo nucleotide biosynthesis is triggered during WSSV infection, we used one of the metabolic contributors to this pathway is glucose as an isotopic tracer. So by using the metabolic tracer with the injection of stable isotope U13C glucose right here, as you can see, it allows us to investigate if glutamine metabolism is triggered and contribute into the nucleotide biosynthesis. And here is the strategy we followed. So as you can see right here, the isotopic labeled metabolite in the U13C glucose treated shrimps were barely changed at the 12 HPI. Suppose that the WSSB barely increased the 13C labeled metabolites in the de novo nucleotide biosynthesis at the WSSB replication stage. And next, at the 24 HPI, the relative intensity of a few metabolites was significantly increased at the 30 minutes post-stable isotope injection, and inferring that the glycolytic flux was delayed during WSSB infection. And subsequently, we further confirmed that de novo nucleotide biosynthesis is triggered during WSSC infection. So we use the other metabolic contributors to this pathway is glutamine right here, and here, as you can see, as an isotopic tracer again. So as we described before, the injection of stable isotope A15 and glutamine into shrimp, it allowed us to investigate if glutamine metabolism is triggered and contribute into the nucleotide biosynthesis. And here is the strategy we followed as described before. So right here, as you see, most of the metabolites representing to the nucleotide biosynthesis will increase at virus replication stage in shrimp hemocyte. So indicating that the uptake of glutamine is contributed to the nucleotide biosynthesis. But however, this effect at the WSSC genome replication stage was no longer observed at the 24 HPI. From here, we infer that the virus has been completed its genome replication and prepared to release at the day stage of WSSB replication. So far, by using the transcriptomic analysis and the in vivo animal experiment, and also for the isotopic metabolic tracking analysis, we infer that the de novo nucleotide biosynthesis, including the pentose phosphate pathway, purine, and the pyrimidine synthesis, should be activated at the WSSC genome replication stage. So next, in order to confirm their importance to WSSB replication, we use the double-strand RNA-mediated gene silencing to suppress the mRNA expression of these critical genes involved in the pentose phosphate pathway or purine or pyrimidine synthesis in shrimps. And these shrimps synthesis in shrimps, and these shrimps were subject to WSSB infection. So as you can see the data right here compared with the two control group, PBS and the luciferase, you can see the viral gene IE1 and the VP28 expression was significantly suppressed in the silencing group. And moreover, the gene silencing of these critical genes also lead to a significant decrease in the WSSB viral genome copies. So, based on all of these results from double-strand RNA silencing, we know that without functional pentose phosphate pathway and the nucleotide synthesis in shrimp, viral mRNA expression and the genome copy were significantly suppressed, so inferring that the pentose phosphate pathway and the nucleotide biosynthesis are important for WSSB replication. And next, as we mentioned before, the RUS PI3K-AKT-mTOR pathway is the key pathway to modulate the WSSB-induced metabolic rerouting. And therefore, by using a series of inhibitors right here, you can see we respectively suppress the factors involved in the RUS, PI3K, AKT, mTOR pathway and see what happened to the mRNA expression of key genes in the nucleotide biosynthesis. So next, here is the result. You can see, I know it is a little bit complicated, so I help everyone to summarize the result. So the key point is that the RUS and mTOR C1, C2 are primarily responsible for regulation of mRNA expression of gene involved in the nucleotide synthesis. And we also believe that the WSSP factors should also involve in this regulation, but we still need to further investigate this possibility. So in conclusion, you can see the WSSP utilize the glucose and the glutamine as the contributors for facilitate the de novo nucleotide biosynthesis. And the activation of de novo nucleotide biosynthesis is important for successful WSSP replication. And in addition, host factors RUS and the mTOR C1, C2 may involve in the negative regulation of WSSP-induced de novo nucleotide biosynthesis. So, last but not least, I would like to thank my advisor Casey and the cooperators and TLab members. Thank you very much for your full support. And thank you for your listening, and I would like to hear any suggestion and the response, any question. Thank you so much.
Thank you very much, Mr. Chen, and good luck with your PhD study. Does anyone have a question to Mr. Chen? So, Mr. Chen, you haven't mentioned, but I think a lot of audience might be interested in what kind of application, from your research outcomes to use in the aquaculture industry.
Thanks for your question. For application, because shrimp disease is as a huge issue for the aquaculture or the economic. So for my investigation, the application will be we are going to select the hallmark some genes may involve in the WSSP replication. So maybe we can select single nucleotide polymorphism type and select the genes that show the low activity for their genes, and then they can because of this single nucleotide polymorphism to decrease the specific genes activity that may cause the WSSP is hard to infect or do the pathogenesis on the shrimp. And we are going to use this method to select the shrimp that can defend the virus infection. So I think it will be like a hallmark.
Yeah, so hopefully your research findings gonna be used for the industry, either selective breeding or some kind of antiviral treatment.
Yeah, thank you so much.
Yeah, okay. You have any question, other people? Probably not. And then I think it's about the time. So I guess this brings us the end of session 3, detection method diagnostic oral presentation. So please join me to put the hands and applaud claps to all the speakers this morning. Thank you.
Thank you so much, and it's my pleasure.
Thank you.